This talk is about understanding artificial intelligence from the perspective of information flow and information fragmentation. So I evolved brains, and I'm going to show you a couple of tasks. This is a block catch task. If you've been around Beacon and you've been around either the Hinsel labs or the Adami labs, you've probably seen this task. There are these blocks that are going to fall from the top, and they're either moving left or right, and they're of different sizes. And if they're a small block, then this agent, who's this paddle down here, should catch them. And if they're a large block, it should miss them. The agent has 6 units wide. It only has 4 sensors, though. It's missing sensors in the middle. So this little 2-size block here, it needs to integrate over time in order to determine that it's a small block. And anyway, we can watch this and we can see that, here are a bunch of 2 blocks that are falling, and it manages to catch them. And here are 4 size 4 blocks, and these are larger than, and it has to miss them, and it manages to miss them. So this is the one kind of a brain that I evolved. Here's another brain. This is a simplified version of the task that Anselmo published, I think last year. This is a path following task where there's a path. There's sort of a trail of breadcrumbs, and along the path there are these right and left turn signals. The trick is that the right and left turn signal values are randomized every time the agent starts on the path, and it has to determine by trial and error whether what signal is right and what signal is left. And if you look up here, you'll see left signal 1, right signal 2, and sometimes it'll say left signal 2, right signal 1. That's just the signal switching. And the way that this agent works is it does a little dance, but it basically makes a mistake. But once it makes that mistake, it now knows what the symbols mean, and it can perform this task. We can look at it, go through this again. It does this little dance to figure out what the pattern is, and then it now knows how to follow the path. So these are not super complex agents, but they're doing some associative learning. They're doing some temporal integration of information. That's what I mean by the sort of the kinds of brains that I evolve. So how should we think about these brains? I have this picture here of like a general brain. It has these blue boxes. These are inputs. It has these green boxes. These are memory. We can call them hidden nodes or recurrent nodes. And it has these yellow nodes. These are the outputs. And the way that these brains work is we program the inputs, and then they have their memory, and this flows into some kind of a process that's sort of like thinking, and it generates an output, and the output is whatever the agent should do. That's the output. And then also the memory nodes are updated. And then every update, we just have to reprogram the inputs, and then just copy the memory back up to the top. And we just run these over and over. And in specific, if we look at, what am I doing? Wow. Oh, I see. I tried to animate things. That was a mistake. Okay, there we go. So if we look at this, this is the same structure right here. The inputs and hidden. Here are the outputs and hidden. And this is a Markov brain. So its process, its thinking is these parallel executed gates. Here's a recurrent neural net, and its thinking is these sigmoid gates that are, so it's fully connected, and the data flows through these sigmoid gates. And but essentially, if I abstract away the guts, they're all just these things. They're all just these very simple, input through process to output. And I'm interested in sort of coming up with objective ways to understand the behaviors, and particularly the evolution of the behaviors in these brains. So we have some tools that we can use. We have some ways that we can look at the behavior. One of these is a state-to-state transition diagram. And if we look at the state-to-state transition, that red node at the top, that's where we start. And then each of the links is labeled with the input to the brain, and it tells us the next state that we're going to go to. And you can just see that, we go from a state of the brain, we get an input, it goes to a different state. And sometimes it's deterministic, it can only go one way, and sometimes it can branch depending on what the input is. These state-to-state diagrams tend to get very complex, and so they can be difficult to analyze. This thing on the right, this is the brain structure, or the connectome. This is for a Markov brain. And if you look, the green circles are inputs, the red circles are outputs, the white circles are the hidden or the memory, and the blue squares are the gates. And you can see how the different inputs and outputs and hidden are connected through gates. And we can see, for example, like one of the things we can glean from this is that input 2 and hidden 1 are simply not being used. They're not connected to, they're functionally, not part of this. But when we look at the state-to-state, like I said, they get to be pretty complex. If we look at the brain structure, the problem with this is it shows the wires, but it doesn't show function. So I know that input 2 is not being used in the algorithm of this brain, but I don't know that the connections that I see in this connectome are actually functional. There may be a wire here, but there may be no information passing through the wire. I'm going to do a little zoom in on the state-to-state, the bottom left corner, just to show sort of what we can glean from this. If you look at this, you see that there's this blue node, and there's a self loop to it. That happens a lot. And then there are these two little branches that come off where it goes down and then comes back up. And those both happen. The number in the parentheses tell us how many times each of those links was traveled. And this is on the Pathfollow task. And what this is one of the, it's one of the cycles that this brain gets into where it's doing left and right and move forward. So this, this input of 0, 1, 0, 0, this is the input that the brain gets when it's on the path and should keep moving forward. And these two symbols are different symbols that it, this symbol and this symbol are two different symbols that it gets when it experiences a turn signal. And it does different things depending on which turn signal it sees. It either turns left or right, and then it moves forward and it's back on the path, and now it's moving forward again. And so this is very easy to understand. But if we zoom out and look at the whole brain, to do that sort of analysis on this whole structure gets to be pretty hectic. Okay, so we can use information theory what I'm supposed to say at this point is this provides two views that allow us to look at how this brain is functioning. We can use information theory to get a different view of how the brain is functioning. I have this one slide I'm just going to read through. I feel like this is like I'm a car salesman and I have to read that thing at the end of the commercial. Shannon entropy proposes that entropy is a measure of uncertainty. Simply put, a very simple system has low entropy and a complex or random system has high entropy. Information in this context can be thought of the ability to predict the behavior of a system. If you have information about a system, you can predict how the system will behave. If you lack information, then the behavior of the system is going to appear random. And information theory provides measures for entropy, that's the uncertainty of the system, mutual entropy or shared entropy, which is the same thing as information. It's how much one system knows about another system. Conditional entropy, which is mutual entropy if you discount some source of entropy. And this formula down here on the bottom, this magical looking thing, this is how you determine entropy. Everything is sort of based on doing this a lot. Representation and smearing are two neural correlates that have been used a lot in the HINSA and Adami labs. Representation is, if you're given a set of salient features about an environment, then representation asks about how much internalized information a brain has about those features. Smearing asks, in a general way, how is that information spread out about the brain? So fragmentation is a new measure, which I'm developing, and it asks where the information is. So there are two ways that we can talk about fragmentation. First, there's a simple form, and that is if we're given a salient feature, some feature about the environment, fragmentation asks what's the smallest number of nodes in an information structure that must be considered in order to know the feature. In order to calculate, actually, I'm going to do this better. So I'm going to give you an example. This is my umbrella example. And the question is, should I take an umbrella? And I have 4 pieces of information. I have the truth of 2 + 2 = 4. I know whether or not I'm currently hungry. I know whether or not it's cloudy. And I know whether or not it's freezing out. And you may note that some of these probably have nothing to do with whether or not I should take an umbrella, but other of them do. So what we can do is we can consider this in terms of fragments. And we can say, I have 4 fragments of size 1, that is 2 + 2 = 4. Am I hungry? Is it cloudy? Is it freezing? Those are my 4 size 1 fragments. Now I have 6. I also have 6 size 2 fragments. I have 4 size 3 fragments. And I have 1 size 4 fragment. And these are all of the different ways that I can partition the information in my brain. And it ends up that if I know it's cloudy and it's not freezing, so if I know the state of cloudy and I know the state of freezing, then I know whether or not I should take an umbrella. Basically, if it's freezing, I don't have to take an umbrella. If it's cloudy, if it's not cloudy, I don't have to take an umbrella. But if it's cloudy and it's not freezing, I should take an umbrella. And this would indicate that the fragmentation about umbrella for this brain is 2. Now we could add weather report. If I have a weather report, well, now the weather report tells me whether or not I should take an umbrella. I don't need to look at the cloudy and the freezing. And my fragmentation on this new brain with this extra piece of information is now 1. I only have to consider 1 piece of information. Okay, so we can extend fragmentation by creating a fragmentation matrix. And with a fragmentation matrix, we consider a list of salient features. In this case, the list is just one thing. It's just, do I take the umbrella? And what we can now do is measure how much each piece of information predicts about the salient feature. So 2 + 2 = 4 tells me nothing about whether or not I should take an umbrella. Whether or not I am hungry tells me nothing about whether I should take an umbrella. Cloudy and freezing. Well, since it is cloudy and freezing, and again, I don't want to bore you with the details, but this is an and because it's an and, cloudy and freezing both tell us 0.31 bits of whether or not I should take an umbrella. Interestingly, if we take them both together, they absolutely tell us that we should take an umbrella or not. But weather report as on its own tells us that we should take an umbrella. These are all fragments of size 1, right? These are my 5 fragments of size 1, and then I have fragments of size 2 and 3, and cloudy and freezing happens to be a fragment of size 2. I didn't list all the other ones because it gets kind of big. But this is essentially what this whole fragmentation idea is about. It is to put this in a way that people who know me will understand. This is not hard. This is in fact, it's very simple. But like me, it's annoyingly repetitive. So it is important to note here that we don't know which is responsible. So if I have a brain and I give it this information, it may be that this brain wires into cloudy and freezing and it simply does not consider the weather report. At which point it's cloudy and freezing that is making the decision. That's the causal link that makes the decision. Whereas if it's looking at the weather report, it may be the weather report. And so simply looking at this, how these pieces of information correlate with whether or not I should take an umbrella, doesn't tell me how the brains actually function. All right, so we can now extend, we now use F, now that we have these fragmentation matrices, we can ask about what parts of a brain predict the next brain state. So if we think of the inputs and the hidden as the current, let's say it's the current brain state, and then we could think of the, well, actually we should look at the output and the hidden as a current brain state, but we get the inputs. And so we could say, okay, if we have the hidden from the past update and we have the inputs, can we use those to predict the next state of the brain? Well, we certainly should be able to, because this process is completely dependent on these inputs and these hidden? More importantly, can we figure out which inputs and which hidden are determining the state of the next outputs and hidden? Guess what? We can. So going back to this example I had before, this is on Pathfollow. We see the state to state. It gets really complex. And we look at the brain structure, and it shows the wires, but not the function. So we know where the connections are. We just don't know how it's actually using them. If we look at this, this is the same brain. Now we're looking at the data flow. And okay, it's not super easy, but let me explain how this thing works. Each of these, whenever we see a node like this H5 down here, and we see that it has 4 lines coming into it, what these 4 lines mean is that in order to predict this node, we have to look at all 4 of these. So it's hidden 4, so memory 4, memory 2, and 2 other nodes have to be considered. I know they're off this week. The number here in yellow is the amount of entropy in that node. So this node only has 0.05 bits of entropy. 01 over there on the right, that has a half a bit of entropy. And then the orange boxes indicate how much relative information this link has about what it points to. You'll notice that, well, actually, I'll bring it up later. But this is this view of information flow. This is kind of what this whole thing is about. It is similar to these views. It's just, again, it's a different view. Now, one thing I can, oh, right. So one thing I can do is I can look at this and what this is showing me, it's showing me the information flow for the entire lifetime. For when we run that Pathfollow, I run it on 16 different mazes, 16 different paths. And this is looking across all of those, looking at all of the different paths. What I can do is I can look just at the last 10% of each of those path analyses. And if I do that, I end up with this flow. So this was the flow of the whole brain. This is the flow if I only look at the end of it. And if you think about it, early in life on the Pathfollow task, which just to remind you guys is this task, early in life, the agent needs to figure out whether or not the left turn signal is a 1 or it's a 2. But later in life, when everybody knows it, its algorithm is actually really simple. And so what this is showing us is that if you look at the whole lifetime, the data flow is actually pretty complex. But if you look only at the end of lifetime, it's actually really simple. And this is actually even simpler because these H7, H3, 0, and 6, they don't go anywhere. This is all just internal processing that doesn't mean anything. This output 0 and output 1 are the only things that are actually active. And these are the things that make the agent turn left and right and move forward. This output 2 would make it go in reverse. It doesn't use it. And so at the end of lifetime, it's only using these 2 inputs, input 1 and input 3, and hidden 4. It's a super simple algorithm. Okay, so there's some more tricks we can do. Connectome validation. So sometimes when we do the information flow, we'll see that we'll get these, the way that I'm plotting it, we'll get these red lines. And what these red lines are cases where we cannot determine which partition is the responsible partition. So this is a case where before I showed the example where it could be the weather, could be the weather report that you watched that told you should bring an umbrella, or it could be the fact that you know that it's raining, that you know it's cloudy and that it's not freezing, and that's why you brought an umbrella. And in this case, I plot these lines as red because I don't know. This is to tell me I don't know. It could be, I know that H6 is determinant of output 3 and determinant of H1. And I know that either H0 or H3 is involved, but I don't know which one. What I can do is I can take the connectome and I can see if there is no wire. So if there, in this case, we're going to see that there's no wire between H0 and H1 and between H0 and O3. And that being the case, we can discount these wires. We say, well, these wires can't happen because if in the brain there's physically no wire there, so that there can be no data flow, and I can now remove them. And so basically, this is like another step where I'm taking the actual brain structure and I'm combining that with the data flow, and I can get a better view of the data flow. And so this gives me a about as simple a view as I can get. All right. So I want to introduce the Nback task. This is a third task. It's a very simple task. We feed the agent a series of bits. So we just like a 1, 0, 1, 1, whatever. And every update, we ask it to report back on the prior n inputs. This is a very easy task for humans to do if they have a piece of paper. It's not easy if they don't. Now, if we consider Nback 5, which is what we're looking at here, I'm going to feed maybe 100 bits to the brain, but on every update, I'm going to ask the brain to tell me what the last 5 bits that I fed it were. And this diagram here on the right is the state-to-state transition for Nback 5. It's really quite complex, and I don't want to do an analysis. I can simply do the data flow, and the data flow for that same brain, the one that made that state-to-state transition diagram, looks like this. The input flows in, it happens to go to hidden 1. Hidden 1 sends it to output 0 and also to hidden 4. Hidden 4 sends it to output 1 and hidden 0 and so on. And the data simply, this is why I'm calling this data flow, because you can see the input flows in and then progressively through the hidden each time it sends some information out. And one thing I mentioned before was that these numbers tell us how much entropy is in the nodes, and these numbers tell us how much entropy is on a link. And what we can see here is that there's 1 bit flowing through this brain, and every single link has 1 bit of information. Now we can. I haven't shown you this. I talked about it, but I didn't actually show it. These are actually fragmentation matrices, and this top one. This is a fragmentation matrix for a brain that looks like this. And what we can see is that these are all the fragments of size 1. So that's 0, 1, 2, 3, 4. There are 5 hidden in this brain. And then these are all the fragments of size 2. And these are the fragments of size 3 and 4 and 5. And what we can see is that for each t-1, these are like when the input comes to the brain, the last input, the input before that, the input before that, all the way up to the 5th input ago. We can see that the 5th input ago is stored in the 0th hidden H0. The last input is stored in hidden 1 and so on. And it's very clean. This brain, like it knows, it has fragmentation 1 on all of these. Basically, every prior input has its own dedicated little memory. This brain here on the bottom, this is from a brain that did not evolve to perfect behavior. And what we can see is that this information is fragmented all over the brain. In fact, to get to perfect information about the t-1, the last input, we have to go out to a fragment of size 3. So this is like really, the algorithm this brain is using is really messed up. And in fact, we don't even get perfect information. Even if we look at the whole brain, a fragment of size 5, we don't have perfect information about t-2. And it gets even worse to the point where the t-5, the thing 5 updates ago, we have a tiny bit of information about it, but basically not very much at all. So this gets us to the idea of encryption. And this is a perfect.
Cliff, do you want questions as you go, or do you want to wait to the end?
No, I can take questions now.
So could you go back to the previous slide?
Yes.
So I noticed that you're not showing what the flow looks like in the imperfect brain.
I didn't record it.
Okay.
So, I mean, I could go find this brain and get the flow.
I guess I'm not as concerned about seeing the specific one, but could you qualitatively say a little bit about what it looked like?
Yeah. Let me pull up something that's indicative. So this is I'm going to just throw some images up. So this is a state-to-state. This is that state-to-state transition that we looked at, and this is the brain that that it came out of. And this is a state to state for, I really wish I had this brain.
So I mean, that one looks perfect, right?
Yeah, that is perfect. This is an imperfect. And you can see it has way less states. And the thing is, it just hasn't learned the later ones yet. Now, I don't have the data flow for it yet, but you can imagine it's not performing all. If you look at these numbers in the blue here, these are the actual values within the individual hidden states. And this brain is not performing perfectly. So it's using these states inefficiently. Yeah, I really wish I had this brain. What you generally see is that you'll get just messes of nodes.
So it convolves different timings of the inputs, and so it has to separate them back out again. And Canto,
yeah, kind of. I mean, you can also think of it like one way to do this is with a data passing, but another one is it could temporally identify 1, 0, 1. Mm-hmm. And say, oh, if I get 1, 0, 1, then the thing I output in 3 ago is a 1. But if I got 1, 1, 1, I have a totally different path to output a 1 3 updates ago. And if I have 0, 0, 1, I have yet a totally different path again. And so basically, it's like it doesn't make the efficient solution to the problem. It doesn't identify the efficient solution. It just makes a whole bunch of one-off special solutions.
I see. Also, just FYI, there's some questions in the chat, though Chris is answering them, about just making sure that folks understand what Nback means exactly.
Oh, right. Okay, I can cover that. Let me put up the chat.
I was the one who asked, and it does make sense to me. I was just confirming my intuitions here.
Oh, okay. All right. Very good. Okay.
I was just assuming that if you were asking, Mike, others might also wonder. So that's, yeah.
So that, you know, I sit here, you know, late at night and I stare at these fragmentation matrices, and they tell me a lot about what's going on in the brain, and it probably means I'm going insane, but that's okay. So what I want to talk about, sort of, this is the last big point, is this idea of encryption. And here, what we're looking at on the right, we're looking at that perfect brain. This is what like this is a minimal structure, perfect performance. This thing on the left here, this is also a brain with perfect performance. But here's where it gets tricky. This input 1 comes in and it flows to hidden 0. Great, no problem. And it's conveying 1 bit of information, and hidden 0 has 1 bit of information. Okay, great. Hidden 0 then flows to output 0, so that it knows what the prior input was. That's the first thing it has to output. And it also flows to hidden 4, and both of those convey 1 bit of information. So far, so good. Hidden 4 then flows to output 1, and that conveys 1 bit of information. It has 1 bit of info. Great. And it flows to hidden 2, so that it can pass on eventually to output 2. But here's where things get really weird. It's not output. Hidden 4 does not predict hidden 2 at all. Knowing the state of hidden 4 independently tells me nothing about hidden 2. There also is this little link of information here coming from input 0 that's also impacting the state of hidden 2. Well, because hidden 2 has these 2 lines coming into it, what it tells me is if I know the state of hidden 4 and I know the state of input 0, then I know the state of hidden 2. But knowing the state of hidden 4 or input 0 independently tells me nothing. An XOR is happening here. So H2 is the exclusive OR of H4 and input 0. And I don't even have to look it up. It's the only way it can be. And in fact, we get a confirmation of this because output 2, this is a perfect performing brain. So output 2 is outputting the correct information. So the data that went from input 1 through hidden is getting output correctly. Note that input 1 encoded hidden 2. On the next update, the information that was in hidden 0, that was in the input is now in hidden 0. And so hidden 0 is used to decode output 2. This is a completely and also it's used to decode hidden 3. This is common. If you look across Nback brains, this sort of simple encryption is common. It's probably, I don't know, I would not be surprised if it's in 20% of all the brains that I look at, maybe more. And if we run, this is, to me, this is somewhat astounding because like, why? Like, why have, this is just extra wires. Well, why is because if this is what evolution finds first, this is what's going to stick. And anything downstream, look, at this point, I have perfect information. Again, no problem. It's totally decoded. And so, you know, this works. It's not going to mess with it. So this is a case of simple encryption. There are cases of more complex encryption. These are also both perfect performing Nback brains with really messed up encryption. So anywhere we see a 0, those are XORs. These 0.3 i's, I don't even know what the logic is here. This is some temporal offset. I don't know what it is. I do want to point out here that, by the way, this H0, this is probably an AND. Well, maybe AND is 0.39 instead of 3.1. Anyway, this is probably an AND because it's 8.1. Also notice that H0 is not part of the algorithm. So this encryption, there is encryption happening here to get H0. H0 is unimportant. But there is some kind of, this is a basic encryption. Input encrypts hidden 1, hidden 4 decrypts output 1, and hidden 3. So that's not that big a deal. But this one is a mess. There's some reverse encryption occurring. It's crazy. So this leads me to my profound statements at the end of the talk. One task's encryption is another task's data integration. So I'm gonna make a call, and I don't think this is surprising to anyone, but evolution is really messy. One way to think about this is encryption is rampant in nature. Whatever solution shows up first, no matter how convoluted, is gonna be what it, you know, what it is. I see no reason why this shouldn't apply to regulatory networks. And I see no reason why this wouldn't explain why GWAS are, it's really hard to find independent genes that convey some function. Why would it be? If the system is not intentionally designed, why would we expect that in a system as complex as a genetic network that we would be able to find single genes that code for a single thing? No, it's going to be a big mess. It's just all encoded. And we should think of it as encryption. We should use decryption methods to try to disentangle how these individual traits are interacting. That would mean having to do a fragmentation across all genes. Good luck. But there's another observation, and I really want to pursue this. This is where I want to take this work. And that is that maybe unintentional data integration, right? All of this unintentional encryption allows for new discovery. And that is, if we look at these brains, this H0 contains some combined temporal state between the input and hidden 4. These contain some integrated state between that's integrating over time, right? Even this XOR here, there's an XOR happening here. The fact that this integrated information is here means that if this agent lives in an environment, or if the environment the agent is in changes, such that that integrated information becomes useful, then this agent already has a leg up. And that maybe brains like this one all the way on the right that can only do the task are going to be fundamentally unevolvable because they simply have no degrees of freedom. They know how to do the thing they know how to do, and if the environment changes, they're fragile and they're going to fail. But these messed up brains here, these guys, well, if the environment changes, they may already have this special sauce to survive. So with that, I will show you this beautiful picture of a recurrent neural net, which basically totally avoided all attempts at making it scrutable, and I'll take questions.
Thanks, Cliff. I see a raised hand. Looks like Charles Ofria has a question.
Hey, Cliff. So I'm wondering about this whole idea of encryption forming randomly, and I agree that whichever way it happens to solve the problem first is the way that that'll get selected for. However, over time, shouldn't there be some level of selective pressures to move away from that sort of encrypted setup? And what I mean by that is if you have 2 bits carrying something down that you have to XOR back together in order to get the answer, that is more fault prone than if you just have that 1 bit, or even send that 1 bit twice, so that in case something goes wrong.
The answer is yes, assuming you can. So I kicked myself. I had the perfect example and I didn't save it. I had an example of a brain performing Nback 8, and the brain was able to do 1 through 6 and 8, but not 7. And we looked at the brain. What it was doing was it was doing a heavy encryption of that bit that was being passed, and it had it in a state so that it could not access it when it needed to output the T-7 output, but it then decrypted it and output T-8. And because it had a limited amount of memory, it could not, it would have to destroy the functionality of 8 in order to free up the bits to decrypt to get 7.
But you do see some reduction in encryption over evolution.
We do, and I can show you an example of this. I wasn't. I have these.
I just wanted to make sure that intuition was correct. That's yeah.
No, and I can show you a really good example of that. So this is an example. Let's decide which image I want to show. Actually, I want to show the on-end. So this is some older work, but it's the same idea. What this is showing is this is showing Nback 8, and if you look on the left of each of these plots, what you see is 0 through 8 on each of them. And what this is this is the T-1, the T-2, T-3, all the way up to T-8. And this is the size of the fragment necessary to predict it. And what we can see is initially, this was a recurrent neural net. Initially, this recurrent neural net, it knows nothing about anything. These values are -1. That means I can't find a fragment that predicts this. But then what we see is that a fragment appears that's very close to size 6 and fluctuates, and this is on line of descent, that is able to predict the T-1. And after a while, we see that there's another fragment of similar size that's able to predict T-2, but the other ones, it can't get to them. At a certain point, it evolves to use a smaller fragment. In the case of the T-1, it's using a fragment of size 2, I think, and in the case of the T-2, it's using a fragment of size 1. And as soon as this happens, as soon as it starts using these smaller fragments, that frees up memory, because this thing only had 8 hidden. It frees up memory, and now it's able to actually learn the next step, and it does it very inefficiently, but then it figures out how to represent that in a smaller fragment, and then it's able to figure out these later ones. And if we look at the fragmentation map for that, we can see, in this case, it's reversed, but what we see is it actually gets these 3. So the I was wrong. The T-1, T-2, and T-3 are all fragment size 1. And the T-4, it has some information in a fragment of size 1, but we have to go out pretty far, in fact, even going to the whole brain, we still don't find a fragment that perfectly predicts it. And then the other ones, we have to go to very, very big fragments to even get to close to perfect prediction. So I think your intuition is totally right. If you look over time, this brain, because it was able to reduce the size of the fragments, which freed up memory, was then able to perform better on the task. but that assumes that there's a pathway to do that.
Awesome. Thank you.
All right, next question is Chris Adami.
Yeah, so actually, rather than asking a question, I wanted to give a little bit of context about this idea of encryption in the brain. So about 20 years ago, I was at a complex systems conference, and I was a neuroscientist who was doing experiments in olfaction on rats. And so they had an experiment where they showed, gave the rat something to smell, and then it would either go in one or the other direction based on that smell. And they were recording from an area of the brain that they knew had to do with olfaction and movement, as a consequence. And he was showing all these recordings from these neurons, and he's saying, I see no signal. This is just random noise. And he says it's a complete paradox that even though I know that these neurons are in an area of the brain that are processing these olfaction signals, it looks completely noisy. I mean, zero information, all entropy. So I raised my hand and said, are you recording from all of the neurons in that area of the brain? And he looked at me like I was some sort of newbie in the field, which to some extent I was. And I said, of course not. We can't record from all the neurons. So I looked at him and says, have you ever heard of cryptography? And then it was his turn to look like he had no idea. And the idea was, of course, that there were some neurons that are key neurons, encryption key neurons. You don't record from them, then just like in the example that Cliff was showing, then it looks like noise, perfectly good, random noise. And that you get to the information only if you include that key neuron. But at the time, neuroscientists were completely oblivious to this idea. I had a discussion with him, and he just looked at me. It's like, how could that be? And I'm like, look, biology is complicated, and if there's encryption, you will not see it by recording from single neurons. But of course, that's what everybody was doing in the field. So my hope is that this kind of analysis at some point will find its way towards people doing this type of experiments in actual, neuroscience experiments, and find the role of encryption in biological brains. So that was my comment rather than a question.
But doesn't that require recording from every neuron?
Well, yes and no. I mean, there are actually areas where you can record from thousands of neurons. Nowadays, people can do it, where you have a pretty good chance of getting a large fraction of the information. Of course, there might be tools, and in a sense, that's one of the things that Cliff mentioned. If we can find computational tools that allow us to sort of find, where these key neurons are, so that we can actually actively decrypt the system, then, it might help us actually find these signals in biological brains also. Keep in mind that when we do encryption in computer science, we have a very good reason for doing that. We want to make sure that there is no computational algorithm that can break the encryption, right? Biology actually doesn't have perfect encryption. And so there might be heuristics that will allow us to come up with a way of finding the information. Even it's encrypted, but not perfectly encrypted. And so that allows us to figure out maybe incremental ways of discarding some neurons that we know, okay, even though they're random, kind of like with the idea of, well, if they're not connected, then they're probably not part of the information pathway. But it's a big problem, not just in neuroscience, but also in cancer biology, also in GWAS, to find the information carrying degrees of freedom if there is rampant encryption going on.
Yeah, so on that, I am less hopeful than Chris. I think it's probably, I think we're just gonna have to wait for like serious quantum computing so we can brute force all of this, because I honestly, the issue is if I run a brain and I get up to maybe 20 hidden, I now have an unsolvable problem. I can limit myself. I can limit the fragment sizes. So I can say, oh, I'm only going to consider fragments up to size 4. And that may actually expose something useful. But if the truth is that the fragment is of size 20 or size 18, it's going to be like days of processing. And if I get to 100 nodes, actually 20 nodes we could probably do. If I get to 100 nodes, I think we're in trouble. And if we get to the thousands of neurons that are typically done in brain scans, right? We have brain scan data with thousands of neurons that looks at a specific brain region. And the question is, how would we apply this? We'd have to do some sort of principal component reduction. But of course, principal component reductions are going to be foiled by encryption.
Yeah, I mean, one of the things to keep in mind is to look at the, to calculate the number of fragments and list all the number of partitions in a set is the Bell number. And the Bell number is such that, roughly speaking, if you add one node, you increase the computational time by a factor of 10 for every node that you're adding. So you might be looking at a day of computing for 10 nodes and 7 days for 11 nodes. And then you go into weeks and months, you know, and years and decades for every node that you add. But I actually believe that there will be a heuristic algorithm. It will require some sophisticated computational methods, but then again, you know, we have developed sophisticated methods in code breaking, you know, where you are in fact using, you know, extra information in order to break the code. So my point of view is we should be looking into you know, decryption methods that have been developed for decrypting codes in order to actually find the information in these biological systems, either brains or regulatory networks, or type of GWAS arrays.
Another challenge of GWAS is the frequency of measurement. Nowadays, they can do like half an hour, sometimes even in the scale of minutes. But genes can turn on and off in 1 second, and that's enough to send another gene into operation, and you completely miss that signal.
I can see that, yes.
So you're saying it's more hopeless.
It could be worse, right?